Thank you very much for the introduction. Just wanted to make sure I'm audible and you can see my slides.
You're audible, madam.
Okay. So, although I had a 90-minute slot, I think I'll finish in about 75 minutes. That's just an estimate. So there is time. If you want to interrupt me, you can unmute yourself and ask me questions if the organizers think that that's okay.
Okay, madam. It's
Yeah.
fine.
Okay. As Madam mentioned, the title of this talk is Leveraging Edge Resources for Service Hosting, and I'll talk a little bit about what all of these phrases in the title mean as we go along. I would like to thank the organizers for the opportunity to speak at this event, and the work I'm going to talk about today has three parts roughly. And this is joint work with three of my students, Lakshmi, Sri Prakash, and Mohit, and my colleague Nikhil Karamchandani, who is also with the Department of Electrical Engineering at IIT Bombay.
Madam, sorry for interrupting. You
Yeah,
may switch off your video because it will reduce the bandwidth uses
sure,
because
sure.
sometimes it is creating problem.
Uh,
Thank you,
is
madam.
this is fine, right? Good. Okay. Okay. So I'll get started. Software as a service instances like social networking platforms and online shopping platforms and navigation apps have had a huge impact on our lives in recent times, and they continue to grow in popularity. This phenomenon has in part been fueled by cloud computing, which allows service developers to use computational and storage resources in the cloud to serve their customers. Even though the computational resources in the cloud are unparalleled in their processing power, serving requests via the cloud increases latency, and this latency is due to the time required to transfer data between the users and the clouds, both way. This latency leads to deterioration in the quality of service or the quality of experience of the user, since all of us tend to be impatient these days and all of us want things to happen quickly. A promising solution to this roadblock is edge computing, where edge computing refers to serving user requests using storage and computation resources at the edge of the network, that is close to the end users. Broadly speaking, the edge is defined as any point between the end users and the cloud data centers. And we say that a service is hosted at the edge if the code, data, libraries required to serve requests for that service are stored on the edge server. If this is done, then answers to user queries can be computed at the edge. In this work, we consider the setting where we have third-party edge resources, where edge resources could be storage, computation, or both. And a service provider can rent these edge resources via short-term contracts. When these edge resources are rented, the service is hosted at the edge, and then requests can be served at the edge. Moving forward, we consider a time-slotted system such that a batch of requests arrive in each time slot. Due to limitations on the computation capacity at the edge server, there is an upper limit on the number of requests that can be served at the edge in a slot. Further, we consider three types of costs. The first, which I've called service cost, is actually the cost of latency. This is the cost the system incurs for the delay in serving in its customers. Since requests served at the edge will have low latency, given the proximity of the edge server to the user, we fix the latency cost or the service cost to zero for requests served by the edge, and a latency cost of 1 unit is incurred for all requests that are served by the cloud service. There is nothing fundamental about 0 and 1, but all these costs could be scaled appropriately and the same analysis will go through. Now, the second type of cost is the rent cost. A renting cost is incurred to host the service on the edge server. So in our setting, this cost is determined by the third party edge resource provider, and we allow this cost to be time varying. The reason we consider time varying cost is, although we study this problem from the perspective of a specific application provider, the effect of the presence of other application providers who might be simultaneously interested in using the resources offered by the edge can be captured through this time varying cost of renting edge resources. More specifically, we consider the setting where the third party resource provider periodically revises the cost of renting edge resources, and this revision can happen potentially based on the current demand. So, for example, from the third party edge service provider, if it has a lot of demand, it can increase its cost. If the demand is low, it can decrease its cost. So, the edge renting cost is an input to our system. The third cost is the fetch cost or the service fetch cost. And this is important because in our setting, we allow dynamic hosting. What this means is that the hosting policy is allowed to change its hosting decision over time. If at a given time the service is not hosted at the edge and the hosting policy decides that we want to host the service at the edge in the next time slot, what is done is the database, the code of the service is fetched from the cloud and installed at the edge. And since there is communication involved in doing this, for each such fetch, the system incurs a fetch cost. So to summarize, slotted time, upper limit on the number of requests that can be served at the edge, and three types of costs: service cost for latency, rent cost for renting edge resources, and fetch cost for fetching the service from the cloud to install on the edge. The algorithmic challenge is to design a hosting policy which decides when to host the service at the edge server. And the goal is to minimize the total cost of service. This total cost is the sum of the fetch cost, the rent cost, and the service cost. The hosting decision can, of course, be changed from time slot to time slot based on various parameters. The service hosting policy knows the rent cost before it makes hosting decisions for the next time slot. It knows the fetch cost, which is the cost of fetching the service from the cloud to the edge. And it also knows the edge service constraint, which is how many requests can be served at the edge in a time slot. And we say that our hosting policy is online because it observes the request arrival process causally, which means it does not know how many requests are going to come for the service in the next time slot or in the future in general. The main contributions of this work are as follows. We propose an online hosting policy, which we called retro renting, RR for short, and we characterize its space, computational complexity, and provide performance guarantees. In addition, we characterize the fundamental limits on the performance of any online deterministic policy. We also focus on the popular and widely studied TTL policies and illustrate that there are certain limitations that the TTL policies have for our setting. And in addition to the theoretical results, we evaluate the performance of our policy using trace data from Amazon and Google datasets and compare it with other policies. This ends the overview of the work and now go into the details. So to make things precise, the following sequence of events occurs in each time slot. We first have request arrivals. These requests are then served at the edge or at the cloud. Then the third-party edge service provider announces the cost, the rent cost for the next time slot. And then our algorithm makes the hosting decision, which could be to fetch the service or to evict the service or to make no change. And this hosting decision is actually becomes a gets realized by the beginning of the next time slot. So step 4, which is the last step in a time slot, determines whether the service will be hosted at the edge or not for the next time slot. I'll now discuss our hosting policy. As I said, this is our policy is called retro renting or RR. In each time slot, RR evaluates if the current cache state is optimal in hindsight. And to do this, it uses the knowledge of the entire arrival and rent cost sequence up to this point. If it finds that the current hosting status is not optimal, the state of the cache is changed. So I'll walk you through formally how this works. So consider this case, which I'm calling case 1, where the service is evicted at time t evict and not fetched till the current time slot t. So I'm using the red portion on the time axis. It indicates that the service is hosted at the edge whenever the time axis is marked in red color. Okay, so up to time t evict, the service is hosted. It is evicted at t evict and then not fetched till time t under the policy RR. Now in time slot t, RR checks if there is a time slot tau between t evict and t such that fetching the service at the end of time slot tau minus 1 and hosting it till time slot t is cheaper than not hosting it from t evict to t. Okay, recall that the thick red portion of the time axis denotes that the service is hosted at the edge in this period. So the second option, where we have a red portion, then a blank portion, and then a red portion again, we call this option B. Now what RR does is it checks if there exists a tau which lies between t evict and t such that the overall cost of service under option B is less than the cost of service under option A. Now if it finds that there exists such a tau, then RR fetches the service, else the hosting status is not changed. I'll walk you through the other case. Hopefully that will clear up any doubts you have about how this works. This is the second case where the service is fetched at time t fetch and not evicted till the current time slot t. So I'm now going to call this option A, and this is the current hosting status under RR. Now RR will now check if there is a time slot tau between t fetch and t such that evicting the service at the end of tau minus 1 is cheaper than hosting it till time t. And this is called option B. If there exists a time slot tau such that the overall cost of service under option B is less than that under option A, then RR evicts the service at time t, else the hosting status is not changed. To summarize, the idea is the following. Based on your current status, look backwards and see if you are doing the right thing in hindsight. If you're not doing the right thing in hindsight, change the hosting status. This is how the retro renting policy works. Now, based on the explanation of the RR policy I just went over, it might appear like the complexity of the policy could scale with time, making it infeasible for implementation because you would have to store the entire arrival and rent cost sequence to determine which hosting decision is optimal in hindsight. While this is indeed true if we implement the policy in a naive way, there is a way to reduce the storage and computational complexity of the policy to order 1. That is, it will not scale with time, using a technique that I have shown on this slide. So the amount of information needed for this implementation is just you need to maintain a scalar delta and update it. And whether you should fetch or evict or make no change can be decided based on the value delta takes in any time slot. And to update the delta, you just have to do 2 or 3 very basic operations. So it's not expensive at all. So order 1 over time. I'm skipping the details because this is not actually our contribution. The paper mentioned in the footnote provided this technique. What we just did is took our RR policy, figured out that it is compatible with this technique and used the technique that they had proposed. The point of showing all of this was just to tell you that although RR sounds complicated, there is a way to make its implementation easy and efficient. I'll now move on to our theoretical results. Our first theorem characterizes the performance of RR by giving worst case guarantees on the performance of RR relative to that of the offline optimal policy. Now, the offline optimal policy knows the entire arrival and rent cost sequence a priori, which means it knows what is going to happen in the future. And we say that this is a worst case guarantee on the performance of RR because the bound that we give in this theorem holds for all request and rent cost sequences. So you give me any request sequence, any rent cost sequence, this theorem gives you a bound on how, in the worst case, how poorly RR will perform. I'm introducing some notation here, which I haven't done before, although we've discussed these quantities before. So M denotes the service fetch cost. Recall that this is the cost incurred by the system to fetch the service from the cloud to host at the edge. Kappa is the edge service constraint. This is the maximum number of requests that can be served at the edge in a time slot. C min, so CT is the rent cost in time t. We consider the setting where CT is at least C min. And I would like you to remember the parameters M and kappa. These are going to be important moving forward. So just to reiterate, M is the fetch cost. Kappa is the maximum number of requests that can be served at the edge in a time slot. CRR and COPT are the costs incurred under RR and the offline optimal policy. What this theorem does is it characterizes an upper bound on the ratio of the total cost incurred under RR and the offline optimal policy for any request arrival and rent cost sequence. The takeaway here is that the performance guarantee, which is the max of 1, this 4 plus blah, 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 this guarantee improves as M increases, and it sort of deteriorates as kappa increases. So the guarantee improves as kappa decreases. Now the proof of this result leverages the fact that RR mimics the offline optimal policy, and we use this to show that RR cannot do too much worse than the offline optimal policy. I'll discuss this in the next few slides in further detail. So I'm only going to be able to provide an overview of the proof given the time constraints. So what we do is we partition time into frames. A new frame begins on each fetch by the offline optimal policy. Here we have a frame where the downward black arrows indicate that the offline optimal policy fetched the service. Now, obviously, between two service fetches, the offline optimal policy has to evict the service at the edge from some point, and that is denoted by an upward black arrow. Okay, so downward black arrow is a fetch, and upward black arrow is an evict by the offline optimal policy. Now we show a series of results. The first thing we show is that RR fetches the service exactly once in a frame. Further, we show that the fetch by RR is before the eviction by OPT, and the eviction by RR is after OPT evicts the service from the edge. Here, the red downward arrow denotes the fetch by RR, and the red upward arrow denotes the evict by RR. Okay, so one way to interpret this frame structure is to conclude that RR is actually mimicking the OPT policy with a delay. And this is not very surprising given how RR works, because RR looks backwards and sees if it has done the right thing in hindsight and corrects if it hasn't. So it's not very surprising that it sort of mimics the offline optimal policy. Now for the further analysis, we divide the frame into 4 subframes as shown here. Now in the first subframe, which I marked with the Roman 1, we see that OPT hosts the service at the edge while RR doesn't. In the second subframe, both RR and OPT host the service at the edge. In the third subframe, RR hosts the service at the edge while OPT doesn't. And in the fourth subframe, neither hosts the service at the edge. It follows that the cost incurred in the first and the third subframes is equal under RR and OPT because the hosting status is the same. So using this and other structural properties of the frame, we bound the cost under RR as a function of the cost incurred under OPT. And then once we have this result for a particular frame, we stitch these results across frames together to get the final result. This is just a proof outline. I skipped all the gory details because it's not possible to convey them to you in this presentation format. I will provide links to these papers sometime in the presentation. If you're interested, you can go look up the details there. Now, going back to our theorem, which I've reproduced here, we have that the performance guarantee improves as M increases. And now that we've seen the proof outline, intuitively this result can be explained as follows. So as M increases, each service fetch becomes more expensive. And therefore, opt does not fetch the service very often and tends to move towards a static hosting pattern. Now, since RR mimics opt with a delay, the fraction of time in which the hosting status under RR is different from the hosting status under the offline optimal policy decreases as M increases. And therefore, the gap in the performance decreases. Secondly, the performance gap increases linearly with kappa. If you recall, kappa was the edge service constraint. This is the maximum number of requests that can be served at the edge. Note that as kappa increases, the edge server is actually becoming more and more powerful since it can serve more and more requests in each time slot. This result suggests that opt is able to exploit this power more effectively than RR, and this leads to a deterioration in the relative performance of RR with respect to the offline optimal policy. A natural question at this point is if this limitation that the performance deteriorates with kappa, or at least the performance guarantee deteriorates with kappa, is this a limitation of RR alone, or would any offline policy suffer the same consequences? So to answer this, we have our next result. This result characterizes the fundamental limit on the performance of any deterministic online policy. So let's take any online policy P, and let CP be the cost incurred under that online policy. This result shows that there exists a lower limit on the gap of the performance between the offline optimal policy, which knows the entire arrival sequence, rent sequence a priori, and any deterministic online policy which has access to the arrival and rent cost sequences causally. The takeaway here is that the performance guarantee for any policy weakens linearly with the edge service constraint kappa. So the idea here is, yes, RR's performance guarantee deteriorates as kappa increases, but so does the performance guarantee for any algorithm. So kappa increasing sort of weakens all algorithms, not just RR. I'm going to skip the proof details for this one, but I'll provide a very brief overview. So the idea here is, since we're considering deterministic online policies, we can predict how they behave given a specific input instance. So the key idea in obtaining this lower bound is to construct a bad sequence for each policy P. And since this guarantee needs to hold for all sequences, if P performs poorly for that particular bad arrival sequence, CP by COPT becomes large. So that is how you prove this lower bound. And the takeaway here is again that the performance gap for any policy deteriorates linearly with kappa. Next, we focus on a specific hosting policy called time to live, or TTL. TTL policies have been widely studied in caching literature, and they're natural candidates for our problem as well, because our problem has some connections with the traditional caching problem, which has been studied through the 1960s. Very briefly, this is how the TTL policy works. When the service is not hosted at the edge and a request arrives, the service is fetched and a timer is set to a value capital L. In each subsequent time slot, if the service is hosted at the edge and no request arrives, the timer is decremented by 1. If a request is received while the service is hosted at the edge, the timer is reset to L. And finally, if the timer decrements to 0, the service is evicted from the edge. Typically, the value of X is fixed. However, there are variants of the TTL policy which adapt the value of L during execution. Our theoretical results are for the case where capital L is a constant. But in simulations, we also consider a variant of TTL where L is adapted over time, which should make it better because it's a more general policy. Our next result characterizes the performance of TTL policies with a fixed timer value L. So CTTL and COPT are the cost incurred under TTL with parameter value L and the offline optimal policy respectively. Recall that the offline optimal policy knows the entire arrival and rent cost sequence a priori. This theorem provides a lower bound on the ratio of cost incurred under TTL and the cost incurred by the offline optimal policy. This result shows that for any fixed value of L, there exists an arrival and rent cost sequence for which the performance of TTL relative to that of the offline optimal policy is, so the ratio is at least as large as shown on the right hand side of this inequality. As you may see, this lower bound actually deteriorates as M increases and the edge service constraint kappa as kappa increases also. So in the next slide, we're going to compare this with the performance of RR and see which of the two do better. So this is sort of a summary of our worst case guarantees. Recall that we made no assumptions on the arrival and rent cost sequence. They could be arbitrary. Our benchmark is the offline optimal policy, which knows the entire arrival and rent cost sequence a priori. The performance metric is the worst case guarantee on the ratio of the cost incurred by a candidate policy P and the offline optimal policy. And if you look at the table below, the second column shows that the relative performance of all online deterministic policies deteriorates as kappa increases. Intuitively, as kappa increases, the edge server becomes more and more powerful. And I think it's reasonable to expect that as the offline optimal policy has much more knowledge than these online policies, it is able to exploit the more powerful edge server better than the online policies. Now, the third column is actually more interesting. The third column focuses on the dependence of various policies on the fetch cost, M. Recall that this is the cost incurred to fetch the service from the cloud to host at the edge. We see that the performance of RR improves as M increases. As I said before, intuitively, this is because as M increases, the service fetch is very expensive. Both opt and RR tend towards not changing the hosting status much. And since RR mimics of opt with a delay, the fraction of time during which RR and OPT have different hosting statuses decreases, and therefore the gap in their performance decreases. Now, contrary to this, we see that the performance of TTL actually deteriorates as M increases. And this is because for large values of M, and when the request traffic is low, okay, so fetching is really expensive and requests are coming sparingly, very rarely. In this case, both RR and OPT are not going to host the service at all because it's not worth paying the rent cost. However, by definition, TTL has to fetch the service when a request arrives and the service is not hosted. So because of this property of the TTL policy, this leads to TTL paying a large fetch cost multiple times, which leads to poor performance. So far we have focused on arbitrary arrival and rent cost processes and provided worst case guarantees. While worst case guarantees have their own utility, sometimes worst case guarantees are too pessimistic for typical input processes. It therefore makes sense to also analyze the performance of various candidate policies for typical arrival and rent cost processes. However, the challenge in doing this is that the definition of typical is not clear and it might be very different for different applications. So, some services might see almost uniform traffic across time, where other services, like for example, Google Maps, will see periodic variations. More people will use Google Maps in high traffic time, like uh, rush hour in the morning when everybody is going to the office, or in the evening when everybody is coming back from the office. So services like Google Maps are going to see sort of periodic variations. So we, however, decided to focus on the former, where the arrival and rent cost processes are IID over time. It's just the simplest assumption one can make. So we started here. So these are our results for the stochastic setting. Okay. Our benchmark for the stochastic setting is the optimal online policy, okay, which we are going to denote by opt-on. The optimal online policy knows the statistics of the arrival and rent cross processes, but it doesn't know the actual sample path. So it's a little weaker than, it's significantly weaker than the offline optimal policy, because the offline optimal policy actually knows the entire sequence, whereas the optimal online policy only knows the distribution of the arrival and rent cost process. So this result provides an upper bound on the cost incurred by RR compared to the cost incurred by the online optimal policy. I have suppressed the actual expression here because it is large and ugly. But sort of the takeaway here is that as T increases, which is the time horizon, the performance of RR approaches the performance of the offline optimal policy at an exponential rate with increase in M. So if M is large and T is large, then the performance of RR will approach the performance of the offline optimal policy. Now we look at TTL and see how it does in the stochastic setting. Our next result provides a lower bound on the cost incurred by TTL as compared to the cost incurred by the offline optimal policy. We show that the performance of TTL deteriorates as the fetch cost, which is denoted by M, increases. So to summarize our analytical results for the stochastic setting, for the stochastic setting, we have that RR performs well in this setting. Its performance improves as M increases. TTL performs poorly for large M. So qualitatively, the results are similar to that in the case of arbitrary arrivals and rent cost sequences. So that sort of ends our analytical results for the first part of this talk. I'll now present some simulation results. In this plot, we consider synthetic arrival and rent cost processes as the details are given on this slide, and we compare the performance of various policies for different values of kappa, which is the edge service constraint. We note that the performance of RR is actually very close to that of the offline optimal policy. Recall that the offline optimal policy knows the entire arrival and rent cost sequence a priori. And we see that even as kappa increases, RR actually performs very well. And in addition, we also simulated a variant of TTL called TTL Online, proposed in the paper given in the footnote. And we see that RR actually, TTL also performs okay, but RR outperforms TTL, and its performance is very close to that of the offline optimal policy. Our next set of simulation results are trace driven. We use two data sets listed on the slide for the arrival and rent cost sequences. We compare the performance of various policies for different values of the fetch cost M. Now, consistent with our analytical results, we see that the performance of RR improves as M increases, and the performance of TTL deteriorates as M increases. To conclude this part of the talk, this problem focuses on a service which is hosted on cloud servers and can also be hosted on a third-party edge server located close to the end users to reduce latency in serving user requests. The algorithmic challenge is to determine how to use third-party edge resources to minimize the overall cost incurred by the system. We propose an online policy called RR and show that the performance of RR is good across various arrival and rent cost models. In addition, we also show that the widely studied TTL policy actually performs poorly for our setting. Now, following this work, we've studied the setting where the service is partially hosted at the edge, such that a part of each request is served by the edge and the rest of the request is served by the cloud service. So I'm sort of changing gears and moving to part two. Uh, if there are any questions, I would be happy to take them now. And if there aren't, I'll move on. Okay, so since there are no questions, I'm moving to the second part of the talk. The key novelty of this part of the work is the option to partially host the service at the edge, where partial hosting implies that a fraction of the database and code for the service is hosted at the edge. In such cases, parts of answers to users' queries can be computed at the edge and delivered at low latency. Partial hosting also uses lesser edge resources. Since you're only hosting a part of the service, you will need less computation and less storage power, and therefore it can lead to reduction in the cost incurred for renting edge resources. Many services are naturally suited for partial hosting since designing services as a collection of independent microservices is something that is growing in popularity. So any service which is designed as a collection of microservices is a very good candidate for partial hosting. I'll give you a concrete example. One example of this type of partial hosting is, let's say you have a news website which uses the edge to cache and load the text of news articles. And this will happen at low latency. And the images and the videos embedded in the news articles are stored at the cloud and delivered from the cloud. So in such cases, what will happen is when a user requests for a particular news article under partial hosting, the text will be loaded quickly since it's coming from the edge. The user can start reading the text. And while the user reads the text, the images and the videos will be loaded from the cloud at a delay. But since the user is already engaged in reading the text, maybe the delay in the video arriving is less annoying to the user because there's something going on the screen. This is one example. Another example would be if we use the, sorry, is there a question? Okay, I'll continue. Another example of partial hosting. Hi, sorry. Professor Das, are you saying something?
No, madam. My internet got disconnected, so I joined again.
I see. So I saw you unmuted, so I thought maybe
Yeah,
you're saying something.
yeah.
Okay. Sorry, I'll continue. So I'll give you another example where this might be useful. So consider Google Translate. Now, if the service is partially hosted at the edge, what we could have is that some language pair translations can be done at the edge and some language pair translations is done at the cloud. Now, if you turn out to be a user of one of those language pairs that is hosted at the edge, your translation will happen quickly. You'll experience low latency and better quality of experience. Whereas if you request for translation of a language pair which is not hosted at the edge, you will be served from the cloud at a delay. So partially hosting something like Google Translate at the edge can improve the performance perceived by some users. Okay, so this is the idea of partial hosting. Now, similar to before, we again model the overall cost of service as the cumulative cost incurred due to latency in service, bandwidth consumption, and renting edge resources. The time is divided into slots. For the purposes of this talk, I'm limiting the discussion to the setting where there is at most one request arrival per time slot, but this assumption can be relaxed at the cost of more involved proofs. So it's not fundamental. When the service is partially hosted, the latency cost, we say, is a decreasing function of the fraction of the service hosted at the edge. So specifically, if rho t is the fraction of the service hosted at the edge in time slot t, the latency cost, denoted by g of rho t, is a decreasing function of rho t. As before, a renting cost of CT units is incurred to host the service at the edge in time slot t. The cost incurred to host a part of the service on the edge server is proportional to the fraction of the service hosted. So if you host rho t fraction of the service, the rent cost you pay is CT times rho t. Further, each fetch of the entire service from the backend server to cache on the edge server leads to a fetch cost of m units. This involves, of course, fetching the database, the code, everything from the cloud to the edge and to store it there. Now, since we allow partial hosting, we might sometimes fetch parts of the service, and therefore the cost incurred to fetch parts of the service from the cloud server to the edge server is proportional to the fraction of the service fetched. So the fetch cost incurred is m times rho t minus rho of t minus 1 plus. Okay. Now, as before, a series of events occur in each time slot. We first have request arrivals. These requests are then served. We actually just have one request arrival, at most one. But if there are multiple, then these requests are served either by the edge or the cloud. Then the third-party edge service provider reveals the rent cost for the next time slot, and then we make a hosting decision for the next time slot. Now here in this setting, the hosting decision is more complicated. You could fetch the entire service, you could evict whatever you have stored, you could fetch parts of the service, you could evict parts of what you've stored. So there are more decisions to be made here than in the first setting where we only allowed either complete hosting or no hosting at all. Also recall that the algorithmic challenge is to design a hosting policy which decides when to host the service and how much to host. And the goal is to minimize the total cost of service. The hosting decision can, of course, be changed from time slot to time slot based on the request arrival pattern and the rent cost. We say that the hosting policy is online, like before, because it only learns the request arrival process causally. It has no idea about what is going to happen in the future. And in addition to this, our policy knows the rent cost just before it makes hosting decisions. It knows the fetch cost M, and it also knows the latency function G. So in the previous setting, there was no G. Here, the additional information our online policy has is this latency function G. One of the key goals of this part of our work is to determine if and when partial service hosting can bring down the overall cost of service. In addition, we are also looking for an online hosting policy with performance guarantees under minimal assumptions on the arrival and rent cost processes. So that is the goal of this part of the talk. I will walk you through the main results. Professor Day, did you have a question?
No, madam, I don't have.
Okay. I heard something. Okay, I'll go ahead. So here is a summary of the main results. Like I said before, actually this is the first time I'm mentioning this. We focus on the setting where only one intermediate hosting level is feasible. So rho t, which is the hosting level, can be 0, alpha, or 1, where alpha is some number between 0 and 1, known to the algorithm. We characterize the fundamental limits on the performance of any online deterministic policy. We propose an online hosting policy and provide worst case performance guarantees for this policy. And we also characterize the setting where partial service hosting is used by our online policy. So it's possible that you have the option to partially host the service, but that option is useless and therefore is never used. So we actually characterize when partial hosting is useful. And like before, in addition to our theoretical results, we evaluate the performance of our policy using trace data. And this trace data was obtained from Amazon and Google datasets. And we compare our policy with various other policies and some other relevant fundamental bounds. I'll start with our analytical results. Our first result characterizes the fundamental limit on the performance of any deterministic online policy. Let CP be the cost under any online policy P. Under these constraints on the rent cost C that are given in the theorem statement, this result shows that there is a lower limit on the gap between the performance of the offline optimal policy and any deterministic online policy. Recall that the offline optimal policy knows the entire arrival and rent cost sequence a priori, whereas the online policy only has access to arrival and rent cost sequences in a causal manner. Now note that in the theorem statement, there are some assumptions on Cmin, and the case where these assumptions are not satisfied, that case is very straightforward, and it's easy to show that a very simple static hosting policy is optimal for that case. And therefore, those cases are almost trivial and therefore excluded from this result. So the takeaway here is, if the parameters are such that the hosting problem is actually non-trivial, then no policy can beat this fundamental lower bound. So the cost incurred by any policy is at least something times the cost incurred by the offline optimal policy. Proof outline again, since the policies we consider are deterministic, we can predict how they behave for an input sequence. So the key idea to obtain a lower bound of this kind is to construct a bad sequence for each policy P. I've worked out one detailed example here. I'll skip the details because this is not the most interesting part of this work. If you're interested in this, I'm happy to share my slides. So what I'll do next is talk about our dynamic hosting policy. Recall that the goal is to decide when to host the service and what fraction of service to host in each time slot. Our online policy for this setting is called alpha retro renting. Alpha here, recall that denotes the alpha denotes the partial hosting status that we are allowed to have. Okay. So in each time slot, alpha RR evaluates. It is very similar to RR. It evaluates if the current cache status is optimal in hindsight. And to do this, it uses the knowledge of the entire arrival and rent cost sequence up to this point. And if not, the state of the hosting status is changed. So for example, consider this case where the service is evicted at T evict and not fetched till the current time slot T. So the gray portion of the time axis indicates that some fraction of the service, either the full service or partial, is hosted at the edge in that duration. This is option A. This is what alpha RR did in this time frame. Now, alpha RR checks if there is a time slot tau1 between T evict and T, such that fetching the full service at the end of tau1 minus 1 and then hosting it till time T is cheaper than not hosting the service between T evict to T. So the thick red portion of the time axis denotes that the service is fully hosted at the edge in this period. So let's call this option B. Alpha RR also checks if there is a time slot tau2 between T evict and T, such that fetching alpha fraction of the service at the end of time slot tau2 minus 1 and hosting it till time T is cheaper than not hosting the service at all. The thin red portion of the time axis denotes that the service is partially hosted at the edge in this period, meaning alpha fraction of the service is hosted at the edge. This is option C. Now, what alpha RR does is if it sees if there is a value of tau1 or tau2, and if there is, then it compares these three options and determines which of the three has the lowest overall cost. If option B is the best, alpha RR fetches and hosts the entire service at time slot T. If option C is the best, alpha RR fetches and hosts alpha fraction of the service in time slot T. If option A continues to be the best, then the hosting status is not changed. So the difference between alpha RR and RR we discussed before is RR only had options A and B. Alpha RR, because it can store alpha fraction of the service, also has option C. So it has more options. It can exploit the third option if that is indeed the best of the three. Now consider the second case. In this case, the entire service is fetched at time t fetch and not evicted till the current time slot t. This is option A. This is the current hosting status under alpha RR in this time frame. Now alpha RR checks if there is a time slot tau 1 such that evicting the service at tau 1 is better than hosting the entire service from tfetch to T. It also checks if there is a time slot tau 2 between tfetch and T such that evicting a part of the service. So initially you had the entire service hosted till tau 2, and from tau 2 to T only alpha fraction of the service is hosted at the edge, and that becomes option C. So what RR does, alpha RR, sorry, is compares the costs under these three options. If option A is the best, it does not evict. If option B is the best, it evicts the entire service. If option C is the best, it evicts 1 minus alpha fraction of the service and hosts only alpha fraction of the service from T onwards. Okay. Now this is the third case where alpha fraction of the service is hosted from T last to T. Again, it compares the other two options and goes with the option that is the best. I'm skipping the details because they're very similar to the first two cases. Like before, based on the explanation of our policy I just went over, it might appear like the complexity of the policy could scale with time, making it infeasible and computationally expensive. And the reason for that is you might have to store the entire arrival and rent cost sequence to determine which hosting decision is optimal in hindsight. So this is indeed true if we implement the policy in the naive way that I explained. However, again, like RR, there is a way to reduce the storage and computational complexity of this policy to order 1. And to do that, we need to maintain 3 scalar quantities, delta 1, delta 2, and delta 3, and update them in each time slot through some simple min, max, addition, subtraction type of operations. And hosting decisions can then be made based on the values taken by these 3 deltas over time. So the takeaway here is that alpha RR can be made efficient, and by efficient I mean its complexity will be order 1 per time slot. I'll now move on to the analytical results. C alpha RR and C opt are the cost incurred under alpha RR and the offline optimal policy respectively. Recall that alpha is the intermediate hosting level that is allowed. G alpha is the latency cost function. Rho 0 is the fraction of service hosted at time 0. And the reduction in the latency cost due to intermediate storage of alpha is 1 minus G alpha. This theorem characterizes sort of, it sort of tells us when partial hosting is useful. Okay, so the key takeaway from this is that if the reduction in latency cost at the intermediate hosting level is less than the fraction of the service hosted, then alpha RR does not use partial service hosting. Okay, so if alpha is greater than 1 minus G alpha, then partial hosting is not useful. That is the takeaway. And further, as I mentioned before, C alpha RR and C opt are the cost incurred under alpha RR and the offline optimal policy. And this theorem tells us that the performance of alpha RR as compared to the offline optimal policy is worst at most by a factor of 4. That is, the cost incurred by alpha RR is at most 4 times the cost incurred by the offline optimal policy. Recall that the offline optimal policy knows the entire request arrival sequence and the cost sequence a priori. Alpha RR is an online policy which does not know all this. But it turns out that even though it has limited information, alpha RR cannot do too much worse than the offline optimal policy. Next, I'll provide a very high level proof overview. This is similar to the proof of RR. However, it's significantly more involved because of this additional hosting level that we are allowed to have, which is alpha. So like before, we divide time into frames such that frame I starts when the offline optimal policy fetches the service. Now note that here we have different types of fetches. We can have a partial fetch or a full fetch. So because of that, there are 3 types of frames. A type 1 frame starts on a full fetch by opt. A type 1 minus alpha frame starts when opt fetches 1 minus alpha fraction of the service. This happens when the hosting level goes from alpha to 1. And then we also have type alpha frames, which start when opt fetches alpha fraction of the service. Now for each of these 3 types of frames, we bound the cost incurred under alpha RR as a function of the cost incurred under the offline optimal policy called opt. And then we use the previous step to obtain an overall bound on the performance of alpha RR. The proof details are quite involved, so I'm skipping those details. I'll now present some simulation results. So we'll compare the performance of alpha RR with RR, which is a policy we've just discussed. It does not use partial hosting. In essence, RR and alpha RR work on the same principles. This comparison will allow us to measure the benefits of partial hosting. In addition, we also plot the performance of the offline optimal policy with partial hosting, the offline optimal without partial hosting, the lower bound on the cost of any deterministic policy with partial hosting, and the lower bound on the cost of any deterministic policy without partial hosting. So we have 2 policies and 4 fundamental sort of results. And we present both synthetic and trace-driven simulations. I'll start with synthetic simulations. So for this set of results, the request arrival process is Bernoulli, and the rent cost process is the ARMA 4-2 process. ARMA stands for auto-regressive moving average. 4 and 2 are parameters of this process. The average value of C, which is the rent cost, is 0.35. The fetch cost is 10, alpha is 0.3, and we look at a time horizon of 2000 time slots. So in this plot, we vary the value of G alpha, which is our latency function, as shown on this figure. And the value of the Bernoulli parameter of the arrival process is this complicated function, P equal to 0.5 times blah, blah, blah. And we've chosen this particular value of P to ensure that the optimal thing to do for all these data points is to partially host the service at the edge. And in right, so in this plot, we refer to alpha RR as RR with partial. I need to update these plots to change the name. We see that the performance of alpha RR or RR with partial is quite close to that of the lower bound with partial hosting for all values of alpha plus G alpha considered. So we see that the performance gap between RR and alpha RR is high when alpha plus G alpha is less than 1, and the performance gap vanishes as alpha plus G alpha become larger than 1. This signifies the benefits of partial hosting and shows that there are limitations to it. So only when alpha plus G alpha is less than 1, partial hosting matters. If alpha plus G alpha is actually larger than 1, then whether you have the option to partially host or you don't, it has no effect. RR with partial behaves like RR without partial, and so do the upper bounds as well as the 2 optimal policies. Now in the next plot, we vary the value of the fetch cost M The values of the remaining parameters are as given on this slide. It's important to note that for this set of results, alpha plus G alpha is actually less than 1. So we expect partial hosting to be useful. And we see that the performance gap between alpha RR and the offline optimal policy with partial hosting actually decreases as M increases. And this is because as M increases, there are fewer fetches, and therefore the difference in that performance goes down. You see that the performance gap between RR and alpha RR or RR with partial is significant for all values of M considered. This illustrates that partial hosting is indeed important when alpha plus G alpha is less than 1. In the next plot, we again vary the value of the fetch cost M. The value of the remaining parameters are as shown here. It's important to note that for this set of results, alpha plus G alpha is greater than 1. And in this case as well, we see that the performance gap between alpha RR and the offline optimal policy with partial hosting decreases as M increases. And we see that the performance of RR and alpha RR are actually very close, almost indistinguishable. This shows that I'm reiterating the point that if alpha plus G alpha is larger than 1, there is no benefit in partial hosting. You can just go with full or no hosting and get almost the same performance. I'll now go to some trace-driven simulations. For this set of simulations, we compare the performance of alpha RR with that of RR, the offline optimal policy with partial hosting, and the offline optimal policy without partial hosting. Note that I'm not plotting any lower bounds here. We use the Google cluster data, which is available open source, to model the request arrival process, and data from Amazon AWS Spot instances to price the model of the rent cost sequence. Links to these datasets are given in the footnote. We vary the value of G alpha, keeping M and alpha constant. We see that the performance gap between alpha and RR and alpha RR is high when alpha plus G alpha is less than 1. And this gap vanishes when alpha plus G alpha is larger than 1. This again signifies that the benefits of partial hosting are limited to the case where alpha plus G alpha is less than 1. I have one more plot for this part of the talk. In this plot again, we vary the value of the fetch cost M. We see that the performance gap between RR and alpha RR actually increases with M for this setting. So to conclude this part of the talk, we consider the algorithmic challenge of dynamic service hosting at the edge in the setting where the service can also be partially hosted at the edge. We propose a computationally efficient online hosting policy called Alpha RR. This policy exploits the benefits of partial service hosting. We show that under alpha RR, partial hosting is not useful when alpha plus G alpha is larger than 1. And most importantly, alpha RR is 4 optimal in the worst case. And in simulations, we actually saw better performance than being 4 optimal. Even beyond alpha RR, we conjecture that the benefits of partial hosting are very limited if the reduction in latency cost at the intermediate hosting level is not more than the fraction of the service hosted. That is, if alpha is larger than 1 minus G alpha, partial hosting has very limited utility. And in the third part of the talk, we're going to stick to the setting where partial hosting is allowed, but we're going to do a different flavor of work where we design hosting strategies when the distribution of the arrival process is known to us. So far, we did not have any knowledge of the distribution of the arrival process. Both alpha RR and RR were sort of blind to the distribution of the arrival process. In the third part of this talk, we'll see what we can do if we knew the arrival process stochastic. Okay, so this is the third setting. We consider a two-state Markovian model for the arrival process. When the Markov chain is in the high state, denoted by H here, the arrivals are Poisson with rate lambda H. And when the Markov chain is in the low state, denoted by L, The arrivals are Poisson with rate lambda L. We expect lambda H to be larger than lambda L. This is of course a generalization of IID arrivals. And we assume that at the end of a time slot, an oracle tells us what state the Markov chain is in. So we know what the state of the Markov chain was in the previous time slot. Here our focus is again on determining if partial hosting is needed for optimal performance. As before, we conclude that the answer actually depends on the function g. Specifically, if g rho is always larger than 1 minus rho for all rho in the interval 0 to 1, then optimal performance can be achieved without partial hosting. And if g rho is less than 1 minus rho for some values of rho, then partial caching or partial hosting can actually be useful. And we'll see when it is actually useful. Now, as a first step in this problem, we model the service hosting problem as a Markov decision process, shown here. The state of the MDP is the arrival rate of the previous slot and the decision taken in the previous slot. The action represents the fraction of service to be hosted in the current time slot T, and the goal is to find the optimal service hosting policy. Okay, so this slide sort of tells you what the MDP is. And now we're going to solve it for a few cases. So here we show the solution of the MDP for the case where 0 is greater than or equal to 1 minus rho. To understand this plot, note that we have M on the y-axis. M is the fetch cost. We have C on the x-axis. C is the rent cost. Here we assume that C is actually a constant. It's a number, doesn't vary with time. Now for various regions in this MC plot, we have ordered pairs, right? If you see the leftmost region, we have written 1, 1. What this means is, look at the region in the middle, which is 1, 0. That's easier to explain. The region inside the triangle. So 1, 0 means that if the Markov chain was in the high state in the previous time slot, rho, which is the fraction of the service your host, is 1. And if it was in the low state in the previous time slot, the fraction of service you should host is 0. So 1, 0 means host the entire service if the Markov chain is in state high, and host 0 service if the Markov chain is in state low. Okay, so this should help you understand what 1, 1, 1, 0 and 0, 0 mean. Now look at the region in the second column from the left where the answer is actually 1, rho. So rho here denotes the hosting status of the previous time slot. So 1, rho means that if the previous time slot had the Markov chain in state H, store the entire service, which is 1. And if the previous time slot had the Markov chain in state L, then keep the same hosting status as you had before. So if high, change to 1. If low, keep it at rho. That is what 1, rho means. So one thing to note here is that eventually 1, rho will become 1, 1. More specifically, once we have one transition from high traffic to low traffic, 1, rho will become 1, 1. And similarly, rho, 0 will become 0, 0 once we have a transition from low traffic to high traffic. And therefore, it follows that partial hosting will only be used a finite number of times irrespective of the starting state. So the takeaway from this slide is that if g rho is larger than 1 minus rho always, then partial hosting has very limited utility, even for the solution of the Markov decision process, which is actually optimal. And the other case where 0 is less than 1 minus rho turns out to be more complicated. It almost becomes analytically intractable to obtain the optimal policy in closed form for this case. This motivated us to design a new policy called arrival-based caching. This policy makes decisions purely based on the arrival rate in the previous time slot. It does not look at the hosting status in the previous time slot to make decisions. So under the ABC policy, we make decisions only based on the arrival rate. That is, we store row H fraction of the service if we observe that the Markov chain was in the high state in the previous time slot, and we host row L fraction of the service if the Markov chain was in the low state in the previous time slot. And we compute rho L and rho H by minimizing the expected time average of the total cost. So that's a simple computation. So here is what the solution to the ABC policy looks like. If 0 is larger than 1 minus rho, we observe that partial hosting is not used by the ABC policy at all. We've divided the MC area into 3 regions. To the left of the triangle, irrespective of the state of the Markov chain, the entire service is hosted, 1, 1. To the right of the triangle, irrespective of the state of the Markov chain, the service is not hosted at all, 0, 0. And inside the triangle, if the Markov chain was in state H in the last time slot, we host the entire service. And if the Markov chain was in state L in the previous time slot, we don't host the service. That is 1, 0. So we see that if 0 is larger than 1 minus rho, under the ABC policy, partial hosting is not used. However, for 0 less than 1 minus rho, things are a little different. We observe that partial hosting is used by the ABC policy in the shaded regions. And if you see the shaded regions, it's basically the region which has some intermediate value of C, and there are more cases when M is small. So partial hosting is useful either when M is small or when C lies in an intermediate range of values. So what we are now going to do is look at some simulation results. And in these simulation results, we're going to compare the policy performance of ABC, the optimal MDP-based policy, RR, and alpha RR. For this set of simulation results, the request arrival process is Poisson with parameter 200 when the Markov chain is in the high state, and Poisson with parameter 10 when the Markov chain is in the low state. The values of the partial storage alpha and G alpha here were chosen based on a curve derived from a real data set. So what we do in this plot is vary the transition probabilities for the request arrival process and compare the performance of various policies. We also compare the performance of, like I said before, RR, alpha RR, ABC, and the Markov decision process. So if you see here in the first 3 plots, we observe the histogram of the hosting status under the 3 policies MDP, alpha RR, and RR as a function of the rent cost C. Here, for this set of simulations, the average number of request arrivals per time slot is 105. We see that for very low values of rent cost, that is rent cost less than 20, the MDP hosts the entire service in all time slots. For higher values, for C lying between 20 and I think about 150, the MDP solution hosts alpha fraction of the service. And for higher values of C, 160 to say 170, the MDP varies between hosting alpha fraction of the service and not hosting the service at all. And for even higher values of the rent cost, C larger than 170, the MDP does not host the service. So these trends can be explained by the fact that as the rent cost increases, the cost incurred by serving requests via the cloud becomes lower than the cost incurred to host the service. And therefore, the optimal policy, which is the MDP policy, moves towards not hosting the service at all. Now, the hosting status under alpha RR, which is the second histogram, has a similar trend, However, the range of values of the rent cost over which alpha RR hosts at least a part of the service is larger under alpha RR than under MDP. RR is a little simpler. It hosts the entire service for low values of the rent cost, and then it does not host the service once C becomes large, 80 onwards. And for intermediate values of the rent cost, it sort of varies between hosting the entire service and not hosting it at all. So as a consequence of the hosting status and the three policies, in the fourth plot below, we see that the total cost incurred for all three policies is actually quite close. However, we observe that alpha RR outperforms RR for low values of C, and RR outperforms alpha RR when the rent value increases a little bit. So there are ranges in which both these policies do well. Of course, MDP is always optimal, so it does better than all these alpha RR and RR. But the thing to note here is the MDP policy knows the entire statistics, and alpha RR and RR don't. So expecting RR and alpha RR to do as well as the MDP policy is rather unrealistic. But as you see here, they don't do too much worse. This is the second simulation result. Again, the first three plots here are the histogram under the three policies. On the x-axis here, we actually have the fetch cost M. We observe that for most values of M, MDP actually hosts alpha fraction of the service. Under alpha RR, the hosting status varies between alpha and 1. And we observe that alpha RR outperforms RR for low values of M, and the performance sort of converges as M increases. Now, unlike the last two simulation results, here we consider the case where the Markov chain is stickier. So the transitions of the Markov chain are less frequent. We again compare the performance of the three policies as a function of the rent cost. The average number of requests here is 73, and we observe that alpha RR outperforms RR for most values of C, and for very high values of C, the total cost incurred under all three policies is the same. And here we note that even though MDP and ABC know the statistics of the arrival process, whereas alpha RR doesn't, the performance of alpha RR is actually quite close to that of the MDP policy and the ABC policy. A similar trend, RR performs poorly for all values of M considered, and alpha RR does significantly better, and its performance is very close to the MDP policy and the ABC policy. For this and the next result, we consider a request arrival process which is very asymmetric in that the probability of transiting from low to high is very low, and the probability of transiting from high to low is very high. And therefore, the underlying Markov chain spends most of its time in the low state. And similar to previous experiments, we conclude that for low values of the rent cost, alpha RR does better than RR. For intermediate values, RR performs better than alpha RR. And for high values, all the policies have similar performance. This is the same request arrival process, but the performance here is plotted as a function of M, and we see that alpha RR outperforms RR for all values of M considered. I'm almost towards the end of the talk. To conclude, we studied the problem of service hosting at the edge. We proposed two online hosting policies. We showed that these policies perform well across arrival patterns and other parameters. We also proposed a third policy, ABC, which knows the statistics of the arrival process. Most importantly, we explored the benefits of partial hosting and characterized conditions under which partial hosting is actually useful and necessary for optimal performance. Thank you, and I'm happy to take any questions you have.
So what do you means, participant, is there any questions? Anyone have any doubt?
Thank you, ma'am, for this very informative talk. Ma'am, I have one question.
Yes.
How to find an optimal decision policy to cache the services at the edge in services like vehicular communication, where the message delivery is constrained by strict latency policy?
Mhm. So what sort of service are you looking to host at the edge? Could you give me an example? Maybe that will help me understand the question better.
Yeah, sure, ma'am. Actually, in vehicular communication or V2X communication, the delivery of information like security information or safety informations, which are very much essential to be transmitted within a very few fractions of millisecond. So, in that case, if there is any kind of accidents or anything which just happened, and that kind of information, it can cache at the edge server so that other vehicles, those who are coming towards that, so they can get the information prior. So like these type of safety services.
Mm-hmm. So, for the type of service you're mentioning, it to me sounds like latency is extreme. I mean, reducing latency is extremely important, right?
Yes, ma'am.
Because old information is almost useless. So for services like this, I think it's a trade-off, right? Whether you want to use edge services and pay that rent cost, or do you want to provide high latency? So if you want to use some of this structure there, you will have to suitably calibrate what number you want to associate to these costs, the latency cost versus the rent cost. For you, I think the latency cost should be higher than the rent cost. And then in that setting, if you use any of these policies that I talked about today, I think you will get something that is optimal for your application.
Okay, and like this MDP policy and the RR policies, we have to test it under increasing latency cost.
Yes, because that is most important to you, right? The entire work sort of assumes that you are telling me what C is, what M is, and what your service cost, latency cost, which I've called one here. I've normalized it to one. You have to figure out what are these numbers for your application. And once you have those numbers in place, the policies will work for you. It
Uh,
may be more art than science coming up with these numbers, because the units are not the same. So you have to come up with some numbers that suit your application. You can't measure them, but you have to come up with
okay.
numbers that suit your application, and then the MDB policy or RR or alpha RR will give you what to do.
Okay. Ma'am, another question, just the little bit out of context, but it is related to caching. So, ma'am, how to deal with the security concerns while doing this caching placement and delivery for any kind of services?
Uh, so this is security from third-party attacks. Is that the kind of security you're talking about, or are agents within the network sort of sending fraudulent information?
Yeah, I'm just asking about the agents within the network, ma'am.
Agents within the network. So, see, typically one way to check for security, if agents in the network are behaving badly, if you have miscreants in the network, what you typically want to do is have some understanding of what typical data looks like, statistically typical data. And the moment you see data that is deviating from the statistical typical, you should have your antennas up and sort of
Ma'am,
conclude that something might be wrong with this data. And
ma'am, for this
sorry, go ahead.
one, no, ma'am. Just you have told about the statistical data, ma'am. In this case, can the time series analysis of this one will help, or
It,
any other kind of data?
so that depends on what sort of data you're looking into, right? If, say, for example, the data is coming from a temperature sensor, then you can have a time series, because any place temperatures have a particular pattern with some variance and standard deviation, and they have a particular rate of change. So you can take all of that into account and have a time series model, And if you see something that is deviating from the time series model beyond the threshold, then you know that something is wrong.
Thank you so much, ma'am.
Okay, thanks.
Anyone else have any questions? You may raise your hand. Okay, hopefully I think there is no questions. Okay, thank you, ma'am, for your nice talk.
Thank you so much.